Very good morning to you all. Today we are going to see the compensation. The next compensation is called integral error compensation. Integral error compensation. Already we have seen one thing, that is in a proportional compensation, proportional error compensation, if you increase k, steady state error decreases 1 by 1 plus kp, 1 by 1 plus kp. As kp increases, that is equal to 1 by 1 plus k. 1 by 1 plus k, that is amplifier gain. If k increases, steady state error will decrease. Already we have seen. But the problem is you cannot increase beyond a certain value from third order onwards. That is one drawback. Another drawback, if you make k equal to infinity, then only steady state error is 0. But it is not possible to have an amplifier with infinity gain, even if it is a first order system. Therefore, the alternate way of removing steady state error is introducing an integrator. Already we have seen, if we introduce an integrator 1 by s in a 1 by s integrator, if we introduce in the forward path, what you will get is, if we introduce 1 by s in the forward path, it will remove steady state error. It will remove steady state error. If 1 by s is introduced in the forward path, it will be removed the steady state error. What you will get here? 1 by ki by s. That is equal to s is included in the denominator. S is included in the denominator. You see that? You see that? S is included in the denominator. If you take LCM, S plus K1, you will get S plus K1 upon S. So, two problems are there. If it is a type 0 system, because of introduction of this S, steady state error will be removed. Steady state error will be removed because G of S become G of S upon S. G of S upon S. Therefore, for a type 0 system becomes type 1 system. Type 0 system becomes type 1 system because of this 1 by S. Kp equal to what? Kp equal to limit S tends to 0. G of S upon S. It is a type 0 system. That's why K by 0 you will get. K by 0, that is equal to infinity. Therefore, steady state error equal to 1 upon 1 plus K, that is equal to 1 plus infinity, that is equal to 0. So, because of introduction of this integrator in the forward path, steady state error will be removed. That is one advantage. But another disadvantage is order of the system is increased. Order of the system is increased to 1. As order of the system increases, the system becomes sluggish. As order increases, the system becomes sluggish. I will tell by this way. If you draw k by tau s plus 1, if you draw the response, it will be like this. Initial slope, if you see 90 degree. Suppose I am having nth order system, s power n plus s power n minus 1 plus etc. If you draw the response, step response for that nth order system, it will be like this. Initially, it is not able to increase. But first order system, how it increases? Initial slope is 90 degree. As soon as you give input, immediately it starts increases. As order increases, there will be a delay. This is called the nth order lag. Nth order lag. As order increases, there will be a delay in output. Nth order lag will be there. So initially it is second order system. Now it becomes third order system, means as order increases, the system becomes sluggish. Pole compensation. or integral error compensation. This is called integral error compensation. Why it is called integral error compensation? 1 by S means integrator. 1 by S means integrator. We are integrating the error. If you put 1 by S in the forward path, what is the input to this? What is the input to this? Error. Error is integrated. Error is integrated. So this compensation can be called as integral error compensation. Integral error compensation. PID controller. PID controller. If we combine all the three compensations, then it is called the PID controller. This is what proportional compensation. The error is multiplied by Kc. What is this? The error is integrated. That is 1 by S compensation. 1 by S compensation. That is integral error compensation. Integral error compensation. PID controller means a combination of proportional compensation, integral error compensation, derivative error compensation. Because the input to the system M of t equal to Kc E of t. Kc E of t. Plus, this is the integral error compensation. Kc by Ti integral of E of t. Plus, derivative error compensation. Kc Kd d by dt. If we give all compensation together, then it is called the PID controller. PID controller. This controller is used in most of the industries. 99% of the controllers are PID controllers in the world. If you combine all the three together, then it is called PID controller. Then how to introduce this PID controller in a loop? This is R of S. Error signal is coming here. Immediately we'll put a Kc here. Here we'll put 1 by S integral compensation. Derivative compensation 1 by, this is equal to 1 by TIS. Derivative compensation is KDS. This is in proportional. This is conventional path. All are added together. That's all. This is given to system G of S. You see that this is integral mode, derivative mode, proportional. That's why it is called PID control. PID control. But we won't put like this. Simply, we'll put like this. For a PID controller, simply we'll put PID control. We won't put the three path. It is understood. All three compensations are included in single. So then we'll put G of S. Most of the industrial controllers are PID controllers only. This is for proportional integral derivative. Or we can say Kc, this is for proportional, this is for proportional, this is for integral, this is for derivative. The error is input, the output is given to system G of S. If you write in, this is in time domain, this is in time domain, this is in time domain. Time domain. If it is in frequency domain, you can write like this. Kc by TIS, integrator. Kc TDS, derivative. So this is in S domain. E of S, M of S, like that. So if we express M of S equal to what? M of S equal to Kc multiplied by 1 plus 1 by TIS plus KD or TD, both can be said, TDS. So this way we can write M of S multiplied by E of S. This is expression in Laplace domain.